What is an observable subspace? Also, this module here, a couple of points are for the exam, but just intuitive parts. So essentially, this is going to be kind of an overview of what observability and reachability are. For the exam, it's important that kind of you remember the intuition behind it and the decomposition parts. So let's go through this. People that did linear systems might recognize some parts. Let's try to read together. Still, discrete time state evolution, because continuous time eventually is going to be the same through Cayley-Hamilton, okay? Even if we don't see it. So the considerations that we do now are for this, but they are valuable also for x dot is equal to ax plus bu, okay? Together, the connection will be Cayley-Hamilton. Anyway, this that expand into this, and etc. And we have the convolution, free evolution, force response. Are we together on this, people? 1, 2, 3. Excellent. Whenever we measure something and we get the output of the system, do we typically measure the whole state? Yes, no, I do not know. No, true. If we have a furnace that is 2000 degrees inside, and we would like to know the temperature inside, and the temperature inside for sure is going to be part of the state, because the the chemical reactions depend on the temperature of the stuff that we are melting. True? Can we measure the temperature inside directly? For sure not, because I can throw whatever I want inside here, is going to melt. True? So typically we have a situation for which our output is connected with the state through, in linear systems, a linear transformation. This C typically is going to be something like 0, 1, 0, 0, 0, 1, 0, 0 something. Okay? You do not measure everything. Are we together, people? 1, 2, 3. Perfect. Think at a car. The state of the car, if we think at a sophisticated system, is not going to be just position and velocity, but it's going to also be somehow the state of the brakes, how much the various suspensions are charged or not. True. Do we have sensors measuring everything? No. We've got sensors typically that give us position velocity. True? Together, perfect. If we want to do state feedback, I do a very brief introduction to state feedback. State feedback means U is equal to minus kx. I allocate my control as a linear transformation of the state. If I want to do this one, in a certain sense, I would require x. But I typically do not have the whole x. I've got y. What do we need? We need an algorithm that transforms this one into an estimator of the state. Okay, are we together? You see the need. We are going to discuss about Leuenberger observers very soon. The important point one that I want to raise in this module here is that sometimes some parts you cannot reconstruct. Let's make a very simple case that you are going to see what I mean. Let's pretend that we have x1 dot, x2 dot equals to minus 1, 0, 0, 2, x1, x2. Y is equal to 1, 0, x1, x2. Are you going to be able to estimate x2 starting from y? Yes, no, I do not know, and do it, think of it, discuss in an intuitive perspective. What would you say, people? Yes, I can estimate x2. No, I cannot. I do not know. You would say no. Why? Because this one is an independent subsystem. True? There's nothing that x2 does that affects x1. And x1 is the stuff that I measure. True? Do you see that it would be slightly different, the situation, if I've got a 1 there? True? Because in a certain sense, in that specific case, x2 percolates in x1. True? Look at this. I'm not showing you the matrix exponential, but just to kind of highlight the intuitions. By itself, if this one was off, x1 would go to 0. True? Do you see it, people? 1, 2, 3? I mean continuous time now. Are we together? x2 by itself, what would it do? Would explode. True? If I see that x1 explodes, is it gonna be because of x1 or because of x2 that is percolating inside? You see that it's x2 that is percolating inside. And in a certain sense, this intuition gives us the idea that we might reconstruct the whole state, even if we measure one state with y, but we might, analyzing the whole evolution of the y, we might get an intuition about also x2. How much are we together, people? From an intuitive perspective, 1, 2, 3. Excellent. Let's formalize this. Obvious, true. If I look at the free evolution, my free evolution that I measure is actually C, the free evolution. Together? Perfect. What does it mean? It means that let's take the system as before. I might have something that does like this is in discrete time, but you got the point. This is the system as before. But if I've got C that is equal to 1, 0, what do I see? I see this evolution here. I see this one. True? Because I see only this part. Together? While, and this is an important thing, the geometrical interpretation that I would like you to have, and that is going to be enough for the exam, is essentially this one. At every point, at every time, this stuff here is a vector. True? You see? Are we together? Now, if I take this object here, this object C is essentially a vector transposed. True? That means I can put it here and think at it that Y is going to be the inner product between this stuff and this stuff. Do you see it, people? What is an inner product between two vectors? It's the projection of one into the other. Stretched. True? And you kind of see that in this specific case of this one, we are having what? We are kind of projecting the stuff. And you see that this evolution that we were plotting here would be kind of the projection of this evolution into this subspace. Together? How much are we together, people? 1, 2, 3. I see some perplexed faces. Other questions? If I was choosing something that was like as C, what would I see? I would see only x2. True? Whenever though I take a C that looks like this one, I see a combination of both. True? Or better, watch out. The Y is going to still be a scalar thingy. Okay? But the fact is that this scalar thingy is going to be the combination of two objects. because it's going to be, for example, if this C is minus 0.3 plus 1.7, it means that Y is in general going to be minus 0.3 x1 plus 1.7 x2. From a math perspective, it's that one, but from a geometrical perspective, it's a projection. Okay, together, perfect. Now, let's discuss about the concept of distinguishability. You didn't do it in ellipsis. You didn't talk about distinguishability. No. What does it mean, distinguishability? If I've got an initial condition, and I look at the free evolution, it means that this initial condition will do something. I've got a certain C. It means that this initial condition will create a certain trajectory. True? Depends here what is the case 1, 0 transpose, but you got the point. True? Now, if I've got this one and this one that both produce the same trajectory in the Y, do you see that you can't have any hope of distinguishing this from this by observing this? Is the concept clear? 1, 2, 3. Very clear, not clear at all, kind of clear. The concept of distinguishability is I have two potential causes that are two potential initial conditions, XA and XB. If XA and XB, I put them here, and I've got the same output here, I don't have any hope. Let's make an example. Let's make a numerical example where we are going to be together. I've got my system that is, again, x plus is equal to 0.5002 x. And then I've got y is equal to 10x. Here x is two-dimensional, true? Now let's write the free evolution. The free evolution is going to be y0 is going to be cx0, true? And y1 is going to be cx1. That is going to be ax0. True? Together? Now let's put numbers. Let's start with x0a to be equal to, let me think, 1, 0. Okay? This one is going to be equal to, you compute it. You compute it. This one and this one, you compute them. Go. By table, per table. And paper. Sorry, people, I was distracted. This one, may somebody help me? So this one is going to be equal to 0.5. This is going to be, sorry, 1. This is going to be 1. This is going to be 0.5. Am I right? True? And if I go to y of 2, this is going to be, I hope you see it. This is going to be 0.25. Together? Perfect. Now, xb of 0 is equal to 1, 2. What do I get here? You compute it. It's going to be the same, true? It's going to be the same. I get the same here. Let's go back here. We have XA and XB that are different, true? Actually, it's something like this in this case. That are different. and they produce the same trajectory on y. You, as a user, do you see x or do you see y? What do you see, people? In the plant, whenever you get a plant that is operating, do you measure x or do you measure y? You measure y. So this is the stuff that you get at your supervisory control and data acquisition system. Given the stuff here, and the boss tells you, is it this one or this one that was the initial condition of the plant? Would you be able to answer? Given this C and given this A? No. You see? Distinguishability means I have a situation for which my system matrices are such that there are some subspaces that for which starting there as an initial condition, I will get the same output. And this means that by looking at the output, I'm not able to reconstruct what was there. Okay? Together? Perfect. So this is the definition of distinguishable states in k steps, because actually it depends also potentially in how many steps you have. There are some conditions. I do not want to enter too much into details. I want to kind of you have this overview of what those concepts mean. Okay? Together, 1, 2, 3. Very much, not at all. Okay, and an important thingy is this one. This happens if and only if this happens. True? To verify if this happens or not, what do we need to check about this matrix here? Discuss. To verify whether we have depth equality to 0. What do we need to verify in terms of rank nullity theorem to C, CA, C, K minus 1? Discuss. So if this is matrix, let's call it O, calligraphic O, are we asking ourselves if determinant of O is equal to 0? Yes, this question means asking ourselves this question. Two, false. Asking this question is very different from asking this question. 3, you do not know. Discuss. Ciao.
Non vuol dire che se il determinante uguale a 0 ha più soluzioni, quindi ci possono essere più combinazioni di A e di B vettori che portano ad avere 0. Cioè, a chiesto se...
Sì,
Era una domanda un po'.
Sì. Tipo, so, what would you answer? What would you answer? I'm very happy, actually. There are some wrong answers. This means here that we have a kernel that is non-trivial. True? If this happens, it means that there's a vector that is non-null that is in the kernel. True? Are we together? The fact that the kernel is different from the trivial one if we have this one square, we have this one square, means that somehow we have 0 as an eigenvalue of this matrix, assuming that it's the one for which we have an it's a kind of a square matrix. Here the notation is a bit wrong. I should have put this one, but it's a kind of similar thing. Are we together that we are not asking ourselves about diagonalizability? We are asking ourselves about a kernel different from 0. That means invertibility. That means eigenvalues 0. Together? Okay. How much are we together, people? 1, 2, 3. Other questions? I see some twos. Means that there are some questions. It's the opposite. It's the kernel has to be. Sorry. My mistake. The kernel. I was a little bit too fast. Let's go back. This one is a matrix. To ask ourselves whether this one is different from 0 is asking ourselves whether this one is not in the kernel of this one. Together? I was a bit too fast. If I want to ask myself whether every potential xa different from 0, different from xb, different from 0, if I'm asking myself, if I've got full distinguishability, that means that for every stuff that I throw inside here, this happens. This question here is equivalent to say, is this one always happening? Are we together? And this means if this happens, or better, this thing happens if and only if determinant of this matrix is different from 0. That means that I do not have 0 as an eigenvalue of that. Are we together? Yeah, I was a bit too fast. Okay, very much together, not at all, kind of. Just to be. I still see some twos. Are there other questions? No. So, going back, I might ask myself whether I'm able to distinguish all the states. To be able to distinguish all the states means that somehow every time that I throw inside the stuff here, I get this one. Okay? This depends on K typically, but after n steps, Cayley-Hamilton will make us have that this one is the biggest matrix that I need to consider. Okay? Because all the other rows are going to be linearly dependent to the other rows, and they will not add rank. Are we together? Perfect. Observability is distinguishability from 0. There is an important thing. Let's make the example as before. A, that is 0.5002, okay? And C, that is equal to 1, 0. If I start from XA equals to 0, 0, or XB equals to 0, 10, given this case, those two are not distinguishable. True? It means that this one is not observable. Okay? Together? This is the formal definition. But it's okay. I think that the important concept is this distinguishability thingy. That happens whenever we have rank deficiencies inside here. You see how things are connected. Whenever we have rank deficiencies inside here, it means that from the free evolution, I cannot reconstruct X. All the X's. Some might, some not. Perfect. Blah, 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 blah. The important part is this one. This one is important as a concept for the exam. Look at this structure here. How is this structure? We have some part that I can observe. You see? And there's some part that I do not observe. And this part doesn't percolate inside the part that I observe. Do you see it? X2, the second part of the state here, doesn't enter into the first state. It means that the second part of the state doesn't enter into a part that I can look at. Do you see it? From an intuitive perspective, people. 1, 2, 3. How are we? Excellent. This is the mathematical formalism. We are missing here something, and we are missing here something. Okay? From a graphical perspective, where was it? Where is it? Maybe it's in the next module. How much are we together, people, before I continue with the next part? 1, 2, 3. Excellent. Do you remember that controllability, we were having that a system was controllable whenever I was able to write it in the companion form, controllability companion form. True? Same also here. So control canonical form was this one, okay, where we have the coefficients A's, coefficients B's, coefficients A's, coefficients B's. Remember the sign, because the sign would be that those ones remain on the right-hand side of the equation. Are you following me? This is called the control canonical form. Observer canonical form is essentially transposing some stuff. A system is observable, fully observable. That means that I do not have rank deficiencies in C, A, n-1 C, if I can write it in this way. Okay? So for the exam, you have to remember that somehow full observability means being able to write things in this way here. And there's an algorithm for getting the T's, but I don't want to bother too much with that. Are we together, people?